Hey everyone, so this is the second lesson on fluid mechanics. As I said, there really is not much of a connection between these first at least three topics in this section. So this is all about fluid mechanics, the motion of fluids. Now, one thing that we want to do is we want to define what a fluid is. See, most people tend to think of fluids as liquids. However, that's only partially true. The term fluid actually refers to any substance that could take the shape of its container, which would not only include liquids, but also gases. So gases are also considered fluids. This is important to note that everything that we end up talking about, we're going to mainly focus on the liquid aspect in the beginning, but everything that we're talking about can be applied to gases as well. So as you know, there's four main types of phases. The first one, solid, fixed shape, fixed volume. The second one being liquid, no fixed shape, but fixed volume. Gas being no fixed shape or volume. Then you have one step above that being a plasma, basically an ionized gas. Um, and then there's some other special ones. So some examples of some special phases of matter would be something like a Bose-Einstein condensate. If you continue on in through Stony Brook and in the physics program, one of the labs that you'll end up doing in senior lab, I believe, is you get to work with superfluid helium. And that's an example of a Bose-Einstein condensate or a superconducting liquid. And then there's also things like the mesophasic materials, things that are kind of in between liquids and solids and end up becoming like liquid crystals. But for now, we're mainly going to look at liquids and gases. Now, usually because of the fact that liquids and gases, fluids, don't really have a fixed shape, that means they will easily be able to move from one way to another. So it has what's called a flow, and this is actually a unique property of fluids, something that a solid doesn't have. So when we talk about fluids, we're going to end up talking about flows of liquids and gases, as we'll see later on. Now, one other thing that we want to mention is that in order to make our life easy, for now at least, we're going to assume that all the fluids that we're talking about are incompressible, meaning that their density does not change. Now, that's not actually the case in real life. You know, if you go into the ocean, let's say, as you get deeper in the water does actually change its density. Mainly because as you get further down, the weight of the water above is slowly compressing the water below it, so it starts getting denser and denser and denser. But here we're going to assume that that's not existing, either because we're looking at a small scale of the fluid so that it doesn't have the weight necessary to actually change the density enough, or just, like I said, ideal case. Now, there's a table of densities inside the textbook. Make sure that you know where it is because you're going to need it to answer any of the questions in these slides as well as homeworks. As I mentioned before, if I require you on the test to do something with density, I'll give you the density. This is not something that you have to bring to the test. Yeah, so here it has all the densities. Now, one thing to note is that the density here is always measured in kilograms per meters cubed. I want to make this note for any people who are coming from chemistry, because I know with chemistry you tend to deal with density in grams per centimeters cubed. So if there were some materials that you knew the density of, make sure that you're aware of the change in the unit. All right. As you know, density is something that's constant for an element when it's in a specific phase. So liquid water has a specific density. Solid ice has a specific density. The equation for density is rho equals m over v. To make our lives easy though, because of the fact that liquids tend to, it tends to be hard for us to measure the mass, or at least not useful for us to constantly be referring to its mass. One of the things that we like to do is instead of doing mass, we tend to use density times volume. These are two measurements that are much easier for us to kind of measure and know right off the bat. Like if we have a block of, let's say, helium gas, we know what the volume is of that because we know what the shape that of the container, and we know what the density of helium gas, so we can use those instead of talking about the mass, which would be really hard to calculate. Uh, Likewise, if you want to talk about the weight of something, of a fluid, we tend to use this equation instead, rho Vg, rather than mg. This is going to play a part, as you'll see in a bit. So here, what we want to do is use the density equation to figure out the mass of an iron wrecking ball. So pause the video, work on this, and we'll go over it in a second. All right, so using all these numbers, we can easily find the mass. We know what the density is. The only thing that we don't know is the volume. Now, if you didn't remember this, this actually is a very important equation to know, is the volume of a sphere. So a volume of a sphere is 4/3 pi r cubed. So we're going to use that using the radius, making sure to convert this into meters. We end up getting that the volume is 0.024 meters cubed. Plugging both the density that we have and the volume, we end up getting that the mass is 190 kilograms. All right. Another thing that we can talk about when it comes to materials, not necessarily just liquids, but just any material, is we could refer to what's called its specific gravity. Now, the specific gravity is a relationship between the density of that material and the density of water. So it's a ratio of those two densities, basically saying how much more dense something is compared to water. Because it's a ratio, it doesn't have a unit. So you can think of, if you want to use an equation, you could think of this as being the equation. The density of an object is equal to its specific gravity times the density of water. So for example, if there's a material that has a density of 4, that means it's 4 times as dense as water. That's all specific gravity means. Now, when we look at this a little bit later on, we're going to return to this in, I would say, probably a few minutes, maybe 5 minutes or so. We'll see that this actually does give us a really nice relationship when it comes to buoyancy. So here's some specific gravities. As we see here, helium has a very low specific gravity, so that means that it's a very less dense than water type substance, while gold has a very high specific gravity. So just to give you a heads up, the thing that I'm telling you about, that I was trying to refer to before, is that with specific gravity, it can actually tell us about how an object floats in water, how much of the material is below the water and how much is above. As you've probably heard, I don't know the exact number, but I want to say you probably heard before that it's 80 to 90% of the mass of an iceberg is below the water. And the reason that's true is because of the iceberg's specific gravity dictates that that amount always has to be below the water. Like I said, we'll talk about that in a second. Now, one of the most important things to talk about with fluids is pressure. Pressure is going to be a driving force, if you will, in this topic. So pressure is the amount of force acting on a surface. The unit that we're using is pascals, which is represented by PA, or in SI units would be newtons per meter squared. So pressure is just force over area. Now, in the US, we use the pressure unit that we use is pounds per square inch, or PSIs. So you're going to need to be able to convert a lot of times on the units in the homework questions from this American unit to pascals. Just throwing that out there. This is the conversion that 1 pounds per square inch is equal to 6.895 times 10 to the third pascals. So whatever the PSI is, just multiply it by this and you get your pascals. And if you want to find the PSIs, multiply the pascals by this number. You know, pretty standard stuff. So here we have another question with the pressure exerted on the ground. Pause the video, work on this problem yourself, and we'll go over it in a second. All right, so they want the pressure. So what we're going to do is use the equation force over area. Now, force is the weight of our person. We have a mass of 60 kilograms, so that's pretty easy to figure out. And we just take that, divide it by the 500 centimeters squared to get this, and then we end up getting the pressure to be 1.2 times 10 to the fourth newtons per meter squared. Now this actually leads me into a very important thing that I feel a lot of people have problems with, and that's converting from centimeters squared to meters squared, or just any unit like that in general. So centimeters, as most people know, a centimeter is 10 to the negative 2 meters. You know, centi literally just refers to this. Now, if you have a scenario where you have this, centimeters squared, technically, that means that the 10 to the negative 2 is also being squared. So the conversion from centimeters squared to meters squared wouldn't just be 10 to the negative 2, it'd be 10 to the negative 4. Likewise, centimeters cubed would be 10 to the negative 6 meters cubed. So basically what this means is if you're one of the people that is just used to moving the decimal place over twice to go from centimeters to meters, you have to note that you have to do that twice for every exponent you have. You don't have an exponent, just do it twice. You have an exponent of 2 here, do it twice 2 times or 4 times. This would be 6 times. So just be aware of that. Like I said, this is something that a lot of people have trouble with, going from centimeters squared to meters squared. You're going to see it a lot, so you want to be able to do it yourself. All right. Now, right now, what we're going to talk about in this section is non-moving fluids. So these fluids are going to remain stationary. So what this means is that the pressure is equal on all sides of the material. If there was one side that had a higher pressure than the other, well, then the fluid wouldn't be non-moving, it would be moving. So we have to, this is definitely important that the pressure is going to end up being the same in all directions. This basically says the same thing. They're actually essentially saying if then. So now another thing is pressure is actually a scalar quantity. It doesn't have a direction. A lot of times though, we sometimes think of pressure as having a direction. That's really more the force that's caused by a pressure, but usually it's also a pressure difference. And pressure will always produce a force that's perpendicular to the surface. Otherwise, you'd end up having movement. All right. Now, we want to show how to calculate the pressure in a fluid at some depth. Now, one thing that I want to point out is I am going to show you in this class a little bit of the derivation on where the equations come from. I mainly do this because I want you to be aware that these equations aren't coming out of nowhere. People didn't just say that, hey, this is the equation we're using, but that it came from one of the previous equations, like one of Newton's laws or definition of energy or something like that. So it came from somewhere. You won't need to know how to derive these equations though. You know, when you take a test, you could just use it and that's it. However, I'm just showing it for that whole, background information of, where is it actually coming from. For some people, it might actually make the concept click easier by seeing this. But if you don't want to know about how it's derived, just sit back and you could turn your brain off for a second. All right, so we're using the pressure formula. So pressure equals force over area. Now at the bottom, we have the weight of the entire fluid over the area. So we're looking at the pressure on this surface. As I said before, it's easier for us to talk about not the mass of a fluid, but its density and volume instead. So we're going to replace density and volume with, the mass with density and volume. And then since we have this, what we can actually do is replace the volume with area times height, because the volume of let's say this square is its cross-sectional area times the height. Well, I have a height here and a height there. They cross out. I end up getting this equation for the pressure, that it's the fluid pressure, the fluid density times gravity times height. Now, this is usually referred to as gauge pressure, or another way of saying is excess pressure. What this really mainly saying is how much extra pressure is there based off of the water. This is not the same thing as absolute pressure, which will end up taking into account all other pressures that exist. You'll see why in a second, why this is called gauge pressure. Now, we can then follow up and say, well, what if there was an additional pressure acting on the fluid? Or a fluid density difference. So what we would do is, again, we can consider a case, and here we have the pressure caused by the two objects plus its weight. So what we end up having is this, we do the same thing that we did in the previous class where we did some of the forces. We had the pressure caused from the bottom, pressure caused from the top, and then its weight, moving some things around, setting these equal to each other. We end up getting that the partial derivative of pressure with respect to the height is equal to negative rho g. Integrating both, we end up getting this. So this just becomes P2 minus P1. This ends up having a Y1 minus Y2 because of the negative, flipping it. And we end up getting this. So basically, absolute pressure is the gauge pressure plus some initial pressure, or what we normally consider it is the atmospheric pressure. So this is what we would use for absolute pressure. The P0 is the external air pressure, and this rho GH is the internal gauge pressure. So here we're looking at this water tank, and we want to know the difference in water pressure. So pause the video and we'll go over it in a second. All right, so difference in water pressure really is just referring to that gauge pressure. Again, it's the difference in pressure. Both up here and over here, the water is going to be exposed to the same type of external air pressure. So we could just kind of get rid of it and only talk about the gauge pressure. So we take the density of water, times it by gravity, times it by the height above the faucet, and we end up getting that the change in pressure is 2.9 times 10 to the fifth newtons per meter squared. Now, again, note the virus. You don't need to worry about this, but we could do the same thing when talking about air. So we can actually ask ourselves, well, how high would we have to go for the air pressure to become half of the atmospheric pressure? Now, I'm going to briefly go through this. So atmospheric pressure, this is actually a good one to note, is given and defined as this. 1.013 times 10 to the fifth pascals is defined as 1 atmospheric pressure. All right. Now we know that pressure has a direct relationship with density. So what we can do is we can come up with a ratio of density at some height over atmospheric density, pressure at some height over atmospheric pressure. So what we can also do is go back to our definition from the before, and we can say, well, this still holds true, that the partial derivative of pressure with respect to some height is equal to this, negative rho g. Take our relationship from up here and plug it into rho. Take the p here and move it over with dp. dy goes on to the other side like this. We don't have to move this p naught over because that's just a defined constant. Integrate both sides between the ground level to some height above in the air. This ends up being the same thing that we got before. It's just, y. Here though, because of the 1 over p, it ends up becoming an ln function. So we get this. If we want to get, since we're looking for the point where it's half the atmospheric pressure, well, that means this ratio of p over p naught is going to be 1/2. So I can just plug in a half there, and I'm just solving for y. Everything else is known. This is the density of air at 1 atmosphere. This is 1 atmosphere. We end up getting that y is 5,550 meters. Now, you can ask yourselves, well, why don't we take into account the change in g as well? See, if you one thing you should remember from before is that as we get higher in the air, our value of g is also height dependent. So technically, when we were to integrate this, normally we wouldn't be able to pull the g out. G would have to be inside this integration, and we'd have to come up with some equation, probably gm over r squared, in order to come up, figure out how this all is affected by the height change. However, we don't have to take that into account. Well, why not? Well, it's because it barely even changes. 5,000 meters is a fairly small amount compared to the change in the gravity. So for example, going to the top of Mount Everest, which is a little bit more, about less than double, I would say, double the height that we were talking about here, the pressure decreases by 1/3, but gravity is only decreased by 0.28. That's barely noticeable. In fact, most labs, when you're finding gravity, has a difference, an error that's significantly higher than 0.28. So yeah, you would barely notice that. All right. Now this is actually a nice thing because this is something I think everyone's done before. So as I'm sure everyone's done, when you're at some sort of restaurant, maybe when you're bored, you probably took a straw you had in your water, put your finger on top, and you lifted it up, and you noticed that you were able to carry a column of water in that tube. Well, the question is the pressure that is inside this tube greater than, less than, or equal to the air pressure outside? And then I want you to think about why. So pause the video, think about it for a second, and we'll go over it. All right, well, if we kind of look at the FBD on this, we'll see that the water has some weight that's pulling it down. So if this pressure was equal to this pressure, then the forces would have to be equal, meaning that they would cancel out and we'd have a net force going down, which is going to pull this down. So it can't be equal. If this was greater, well, that would just mean it would overpower the air pressure's force, so it would go down. So this would have to be less than. So this is kind of like the work saying that the pressure inside the straw is actually a little bit less than the air pressure. Now, this actually makes sense when we think about how is it that this had a small bit, how does this have a lower air pressure? Well, when we put our finger over there, we created a vacuum. And when we lifted the column and lifted the straw, what you probably didn't notice is that the column of water actually did fall a little bit out. So the volume of air expanded a bit, which means that the pressure ended up decreasing. This is something that we're going to talk about when we get to the thermo section, that there's an inverse relationship between pressure and volume. So when the column of water inside the straw kind of shifts down a bit and increases that volume, it decreases the pressure. So that's what's allowing for the water to actually be taken out. All right, so now what we're going to talk about is a little bit of Pascal's principle. So Pascal's principle is basically saying that when an external pressure is applied to a fluid that is confined in some sort of material, then the pressure at every point is going to increase by that same amount. And this is the main concept of hydraulics. So you have a little pin over here. You apply a force on this small surface pin. It gets a pressure, and that pressure goes all the way through and equals the pressure that goes out over here. And this ends up giving us a scenario where we can actually get a huge amount of force by putting in a little bit of force. This is how brakes also work. It's the same idea that we apply a pressure on one end of the fluid goes all the way through and pushes on the other end. And typically will probably exert a force greater than the force that we're exerting. So this is just showing that the ratio, so because the pressure in equals the pressure out, we can say this, that ratio of force over area equals force over area, or we can rework it like this. It basically means that if we want the force that we put in to increase by a certain amount on the other end, then we want the ratio of the areas to also equal that. So I want the force to double whatever I exert, while I want the area on the other side to also double. This is just another way of doing mechanical advantage. So here is basically saying that we can lift a car fairly easy by having a pin on one end that's 20 times larger than the input pin, and that would exert a force 20 times larger than ours. So a 204 pound force can lift a 4,000 pound car. All right, so we have a bunch of tools that kind of use this concept to measure pressure. I'm just going to briefly run through these. So one of the tools is called an open tube manometer. Now, basically the way this works is you have this little loop of pipe, I guess. Inside is a liquid. It's open at both ends. One end is experiencing air pressure, and then the other end would be connected to whatever you're trying to measure the pressure of. One of my former students said that they use something like this to measure plane tires, so we'll just go with that. So this would go into the end of the tire that they're trying to measure the pressure of, and the difference in the pressures will cause the water to be pushed down on one end more than the other, which would give a height difference from here and here. And we can use this height difference to figure out what the pressure is coming in over here. Because of the fact that height of the liquid is being measured for the pressure, a lot of times instead of using pascals for measuring pressure, a lot of people will end up using things like millimeters of water, millimeters H2O, or millimeter of mercury, also called a torr. Note that in a second. So yeah, these are some additional units that you'll see. And it comes from how we can, some of our more basic ways of measuring pressure. Now, 1 atmosphere is about 760 torr. So that's another conversion that you can note. Again, sometimes the homework questions will have units in torrs. Now, there's another tool called the mercury barometer, invented by a guy named Torricelli, which used atmospheric pressure, which was able to measure atmospheric pressure by measuring the height difference of Mercury. Torricelli, height of Mercury. Ah, there we go. So basically, same thing. You have this like liquid mercury on the bottom. You have it exposed to air. And then in the middle, there's this vacuum tube that the mercury can go into. The air pressure would push down on the surface and push the mercury up into here. And the height that the mercury reaches would result to the amount of pressure exerted. It turns out for Mercury, the height that it reaches is 76 centimeters. So one atmosphere was 76 centimeters, or 760 millimeters. Remember, torr is millimeters of mercury. So yeah, we end up getting the same thing, and we can actually make sure that this is equal to 1 atmosphere by using our gauge pressure equation, plugging in the numbers, and we get that the atmospheric pressure is, 1 atmosphere. This is another one, aneroid gauge. Again, same idea. Air pressure pushes down on this flexible container, causes these beams, levers, I don't know what you call it, to move down, and then this will just shift side to side. Now, the most common gauge pressure that everyone's probably used before, again, works the same way. You put one end into the tire. The difference in pressure causes this pin to go up, and the amount that it goes up, that's used to find the atmospheric pressure. Again, this is actually why. Sorry, this is not to find atmospheric pressure. This is find the excess pressure inside the tire versus the atmospheric pressure, because again, the atmospheric pressure is pushing down. Now, this scale reading would give us the amount of pressure in that tire. This is why we call that gauge pressure, because again, when we use these materials, it's called a gauge. So there you go. All right, now I want to talk a little bit about buoyancy. So as you know, some objects float while others sink. Well, we could think about what causes that. Well, as you know, it's mainly caused by density, but realistically, it's caused by what's called buoyant force. So a buoyant force is what allows objects to feel lighter and float, which is caused by the difference in the pressure around the object that's that's displacing the fluid. So the way we do this, again, same idea. We have a pressure on this end and a pressure on this end. So that means there's a force here and a force over here. Well, the net force, as we can see from the diagram, there's a net force pushing this up. So if I want to know what the buoyant force is, it's going to be the difference between these two forces. Well, from my equation, I know that the force, the force is rho g h times the area, pressure times area. So I take this, and the height is going to be the height difference, the difference between the height here and here. So I end up getting this. Well, we know what area times height is, it's volume. So what that means is the buoyant force is basically equal to the weight of the liquid that got displaced. That's actually a pretty nice and easy thing to think of. That if we have, let's say, a 1 millimeter cubed object, so 1 by 1 by 1, the weight of water that got displaced from submerging that material, that gives us the buoyant force. So Archimedes' principle basically states that this idea that the buoyant force on an object is equal to the weight of fluid that's displaced by it. All right, so here's a question you can work on yourself, and we'll go over it in a second. All right, So here we have a 70 kilogram statue. We want to know the force needed to lift it. So again, it's important to write draw an FBD. Of course, I have a diagram of the FBD here. So we can see that we have a force here, a buoyant force also going up, and we have the weight going down. Now the force that is needed to lift it has to be at least equal to the difference between the weight and the buoyant force. All these forces would have to at least equal 0. So that's what I'm going to do. So my applied force plus the buoyancy force equals minus weight equals 0. Moving everything to the one side, plugging in mg for the weight of the object, and plugging in rho vg for the buoyant force. Plugging my numbers in, I get that the force that I need to apply is 390 newtons. Okay. Again, I had to make sure to convert this from centimeters cubed to meters cubed by moving it 6 times to the left. Note this from before, centimeters cubed, so I would have to move the decimal 6 times, and that's where it goes to -2. All right, so I'm gonna stop the video at this point. We'll continue a few more questions with buoyancy in the next one, and then we'll talk about moving liquids. All right, see you later.